Come on in, take a seat. Parents, please grab a copy of the Physics Major newsletter and read all about your students. I'm Lynn Kaminsky. I am the outgoing chair of the Department of Physics and Astronomy. You'll see an article about that as well. I am very pleased to welcome you all here to our capstone presentation. We do this every year. We've been doing it for quite a while now. And it's really our most proud moment as faculty. And hopefully, as parents, you will also feel equally proud or even more proud of your students because they work really hard all semester, practicing, revising their slides, practicing some more. And I think the results are going to be worth it, and you'll get to hear from them all in alphabetical order as we proceed. And now it is my pleasure to turn the show over to Dr. Scott Severson, the incoming chair of the department, and he's going to just keep everything organized and keep us on schedule.
Thank you, Lynn. Thank you very much. Couple of notes. This is a long program, but it's so exciting to hear the individual students. We do have a music recital next door. So this isn't 100% clear, right? So we're going to ask everyone to use, we have our professorial voice, so we're definitely going to be asking our students to use that as well. And we'll check in on this. I'm probably going to have one of us check on this. I wanted to give one administrative thing. There will be a break and there will be light refreshments. And so we're going to, on the either side of Weston here, depending on our timing, we'll take a break. My preference is that we go through Weston, then take this break. It depends on when the food gets set up, but we'll take a small break. We were interested in, during that break, getting a photo of your children, the students, our students and faculty here today. We also have a tradition when in our regalia, so in your cap and gown, we take a photo. So this was sent out as an email, and I know everyone's going to be organizing, and I believe the students, you have to be in Schroeder Hall tomorrow, but we want to meet at noon then in this area between this ticketing area and Prelude Restaurant at Weil Hall, okay, for a quick photo in our regalia. But we'll try to get some photos in the break today. All right? I think that's it. Is there any questions on that meeting amongst the students? No, we're good on that. So I have one other thing that I wanted to do before we get started. Dr. Kaminsky mentioned that she has served as chair for 15 years. So I went into the archives, and one of the things she mentioned is our newsletter. And of course, this is the newsletter from 15 years ago announcing Lynn was to be the chair of the department. And under her stewardship, this whole capstone, this development for the students has taken place. There's been just tremendous progress over these 15 years. So we were talking as a department, what do you do for someone who has done amazing things and developed over 15 years? And she might understand why in the idea in the department that we might think that something that's aged 15 years might be a good gift. But thank you, Lynn, for all that you do.
I have a feeling that Tom Target had a little bit to do with the actual show.
So that's from the department, and of course Tom's very good taste, palate. He's picked out something exceptional for you. So with that, we'll begin with our first talk. That's Scott Allred, and his advisor, Hung Tao Shi, will be introducing him.
Okay, thank you all for coming. It's a really great pleasure to introduce our first student speaker. So I came to know Scott about 2 years ago, I think when he transferred to SSU from Santa Rosa Junior College. So he decided to work on something that's really, really small. It's a pretty hard research field anyway, so it's a teamwork. And so I really want to recognize the other team member, Mackenzie Hunt. So thank you so much for all the help. All right, let's put our hands together to see what.
Is this on?
You would need to project.
Okay.
This is for the recording. I would have you clip that to your pocket and clip this to your shirt. And I think the best standing position is somewhere there. Thank you.
Hello everyone, my name's Scott Allred. I'm here to present my research on the synthesis of nanowires. Mackenzie Hunt is my research partner and Dr. Hung Tao Shi is my faculty advisor. So with the basics, what is a nanowire? So a nanowire is a really small wire. A nanometer is 1/1000th of a meter. And so to put that in perspective, this is a human hair with a nanowire sitting on the front of it. So the nanowire here is 1,000 times smaller than a single strand of human hair. Really cool. So why are nanowires important? Nanowires, the research in nanowires has been shown to improve solar efficiency and also to increase the data storage density, right? We keep accumulating data on Earth and we need to store it somewhere. So high density storage is largely beneficial. So this is how it works, right? How do you make a nanowire? Well, you have to make a nanopore, you have to make a mold. And so we start by cutting a small piece of metal, a little piece of aluminum, and then polishing it as much as we can by hand, so down to 8,000 grit sandpaper, very smooth. And then we do a chemical etching process called electropolishing to make it even smoother. And so we start out, we're just trying to make this very smooth surface. The reason why this needs to be smooth is because you need to grow these very uniform nanopores, right? So we do a multi-step anodization process. So the first and the second anodizations are basically there to form really uniform dimples in the surface of our metal. And I'll go over this a little bit more in detail. Finally, we do a third anodization, our final anodization, which grows these uniform nanopores on the surface. After that, we deposit nickel into these little tiny pores, these little tiny holes, and we end up with a wire. So one of the biggest problems working in the nanoscale is that you can't see anything that's going on, right? An optical microscope maxes out about 6,500 magnification, and we're looking at things at 200,000. And so we have to use a scanning electron microscope to see what's going on the surface. Also, our machine has an energy dispersive X-ray detector, which basically lets you determine the atomic composition of whatever is being detected. So this is our electrochemical cell. This is where all the magic happens, right? And so it has a Teflon wall, an aluminum base, and a platinum electrode. Our cell, we fill a solution and then we apply current through it. So current flows through like this or like this, right? So now we're ready to get our sample ready. This image is of a raw piece of aluminum, so it's very, very rough, right? You can see here there's divots and all these problems on the surface. So we start sanding, we sand all the way to 8,000 grit sandpaper, right? After that, we electropolish. So electropolish is basically, we take EP fluid, an electropolishing fluid, and apply 60 volts direct current to that. And so what this graph is showing you is right in the beginning, the surface is very rough. And so lots of current is flowing. And as the current smooths out the surface, it doesn't flow as well. And so over time, the current drops. So this is an image that we took. On the left side, you can see it's mechanically polished. It looks not as smooth, not as uniform. On the right, this is electropolishing. Now this is something you can't really see with your naked eye. You can look at it and they both look shiny, but there's a huge difference. So now we're ready to anodize, and what anodizing is basically an accelerated rusting process. So we're applying oxalic acid solution at 40 volts direct current. And what that does is the aluminum and the oxygen form oxide on the surface of the aluminum, right? And so oxide is non-conductive. And so the best way to interpret this current versus time graph is in the very beginning the current drops all the way. So you have this conductive piece of metal, right? And then all of a sudden there's this oxide layer on top, covers the whole top. No current can flow. And then you see this little bump here in the middle where the current starts to move up. And that's where the nanopores are starting to form. The electricity is breaking through that oxide layer and finding weaknesses and making this ordered structure. And so this is a nice picture. This kind of shows you the sample, and then we're growing little oxide nanopores on top, right? This is a picture of what they look like, and this is a 35,000 magnification. And so after that, the next step is to wash all that oxide off. So basically we dissolve all the oxide on the surface here, and what we're left with is these tiny little dimples. So the dimples are really important because this first round, all the nanopores were maybe a little bit random, and so now we do another anodization. And so the second anodization, we get these longer nanopores coming out of the top here, and they also come a little bit deeper. So it's a little bit more uniform. After the next acid wash, we have these really nice dimples here, these nice uniform dimples, which let the third anodization just come with these beautiful organized nanopores. There is one problem. So if we had our choice, we would grow these oxide pore walls just straight off the piece of metal with a conductor at the bottom, but the oxide forms also inside of here. And so what that does is it disrupts the electric flow when we try to deposit the nickel wires in. And so we have to get rid of that layer. So to thin the barrier layer, we complete one more anodization. And this time, we step the voltage down slowly over time. And what that does is it causes this reaction to run in reverse. And so instead of depositing, it slowly takes little pieces of the oxide back into solution. And so what you end up with, this is an image prior to thinning. And so the average pore diameter is about 80 nanometers, 80 billionths of a meter. And after, we have pores around 90 nanometers. And so as the barrier layer is removed, so is some of the pore walls, which is how we judge the thickness of that barrier layer at the bottom, right? So this disappears, and now we're ready to deposit our nickel. So the way we deposit nickel is slightly different. When we anodize, we apply a direct current, constant charge on here. But for the nickel, that doesn't work. So what we do is we build this waveform. So we do a small negative pulse followed by a small positive pulse. You can see that right here. To accomplish this, we have to use two waveform generators, one doing the negative pulse, one doing the positive, and we have to sync them up. So this is only 10 milliseconds altogether, 8 milliseconds of negative, 2 milliseconds of positive. So the reason why we have to use pulse deposition is because if you think about, you have this tube and you're trying to get all these nickel ions down into the bottom. You're trying to get them deposited in there. Well, once they start to deposit, then the solution becomes deficient in those nickel ions, right? You run out of them. And so we do a small negative pulse. It starts depositing those the nickel ions, and then the quick little positive pulse interrupts that process. And then beyond that, we wait 1 second in between every pulse, and so that gives the solution time to come back to equilibrium. And so this is our first deposition. This is the surface. The screen's a little bit small, but I hope you can see. So what you can see is the pores look like they're filled in. We didn't get a completely uniform distribution, but there definitely was some nickel deposited on here. And so what we did next was, all right, maybe we need to do it longer. Let's see, we did 3 hours this time. And so this just was a total mess, right? There's nickel everywhere. You can't, right? So now it's, what do, right? You've done this twice. So you cut the sample open and you see if you can see those wires that grow up. And so we did that. And so this is the aluminum sample. It's pretty thin. This is, 100 microns, so 100 millionths of a meter. It's mostly aluminum, but on the very top is that oxide layer. That's what we've been growing. And so this is a picture that we got that shows those really ordered nanopores that are going vertically down into our sample. And then we were lucky enough to find some nickel nanowires. And so these are little 80 to 100 nanometer little nanowires, right? To analyze these, we use the EDX, which we're basically taking a look at the X-rays that are emitted off this to determine the atomic composition. And so what we found was, in this small region, we had 76% aluminum, 15% oxygen, and 8% nickel. So this is the evidence that we actually had nickel down in those pores. So what's next with this research, right? The next thing we can do is remove the aluminum substrate. We want to get in there, we want to isolate these wires, we want to study their magnetic properties. Also, during our electrodeposition, we're only doing a 10 millisecond pulse, which is so small that we can't record the current as a function of time. We can only see it on an oscilloscope. So we also want to devise a system where we can read that. And also create a reproducible method. Probably 30 samples we've run through, we only got nanopores on one of them, so it's definitely difficult. I want to thank Mackenzie Hunt in the back, my research partner, for grinding it out, Dr. Shee, Steve Anderson, Ryan Brown for all your help, and thank everyone for being here today. Thank you. Yeah.
And we're running these. We're going to be limiting their talks to 12 minutes, which
How long is
Scott
it?
did fantastic. I think it was 10 and a half or something like that. But that gives us some time for questions. Between every talk, we want to get questions for the speaker. So please, anyone? Go ahead.
What was one of the most difficult portions in completing your research?
You know, you just need such a high level of uniformity between samples that it turned out, I don't think I mentioned that our aluminum is 99.999% pure. That was what we started with. And so when we electropolished that, we ended up polishing through it and finding little divots underneath the metal that are caused by when the metal was formed, when they put it together. And so we had to switch to an even higher purity of aluminum. So 99.9999% aluminum is more expensive, right, to actually get results. So it's really finicky, and you can't tell. So every step you have to go look in the SEM to see what happened. And so it's incredibly time consuming. So that was the most difficult part. Yes?
So once you create the nanowires, how do you store them before you use them commercially?
You know, commercially they're generally stored in solution. There's a couple different ways that they make them. This is only one of them. You can also make them chemically out of different elements. And so for these, basically we'd use mercury, and you dissolve the oxide, you dissolve the aluminum, and then you're left with the nickel. And so beyond that, I don't know, because it would be very small. There'd be billions that could fit just on your fingertip. Yes?
How would you extract the nickel wire from the aluminum if you were going to use it?
Exactly that same process. So you basically dissolve everything but the nickel. That type of thing. Yeah. Somebody in the back? Please.
Yeah, how many atoms thick is each wire in diameter?
Atoms thick. What are we calling an atom these days? An angstrom?
What?
Right, so a nanowire is, this is 80 times 10 to the negative 9, and so that's 10 to the negative 10, so what would that be, 100? Or 800, about 800.
Okay.
Yeah, pretty small. Thank you very much.
Let's thank our speaker.
Feels good.